Hello everyone, and welcome to another very exciting See the Change USA webinar. Today we're going to talk about part 2 of a 3-part series talking about Newton's Laws 1. If you missed part 1, you can access those sessions either on the physics lab under Newton's Laws 1 teacher content training, or you can access that on the official See the Change USA Edmodo group. My name is Vincent Weiss. I'm the manager of product and training development. And a few housekeeping items. So first, for this webinar, there will be no audio or video. You will not need it. So if you happen to turn on your video, go ahead and switch it off. And to communicate, we're going to use the chat box feature. So if you put the cursor at the very top of the screen on a little drop-down menu, comes down. Over on the far right, there's an ellipse. If you click on that ellipse, you'll see a chat box option. Click on the chat box, and then you'll see a chat box, and you can immediately type in that, ask any questions anytime during the session. And we'll also have a question and answer session at the very end, so you can answer questions then. And this session will also be recorded, so you can access this recording on both the Physics Lab and the See the Change USA Edmodo group, and we'll talk about where you can find those at the very end. And also the PowerPoint for this will be made available on the See the Change USA Edmodo group. So if you're not a member of that group, we'll show you how you can quickly join the group and get access to all these wonderful materials. So the purpose of this is, first and foremost, to build your confidence in physics. You are all wonderful science teachers, but what we want you to become is wonderful middle school physics teachers. We want you to be fully confident because we believe the more you know physics, the more you're going to enjoy it and see its beauty. And the more you can see its beauty, the more enthusiasm you're going to have in the classroom, and then your students are going to love it as a consequence. And also, we want you to want to help you bring some of these really high-level physics content ideas to the middle school mind. So throughout all of this training, we're going to throw in tips and tricks and different ideas, and from ways you can explain some of these very difficult physics concepts to middle schoolers. So who is it for? It's for teachers looking to take their students to a deeper level of understanding. As I said, some of the content we're going to go through is higher level, but it's really, really good stuff, and it will help you push your students to a really deep understanding of physics so that when they get into high school and start seeing these concepts, it'll not be brand new to them, but they will be masters at it already. It's also for teachers who do not have an extensive background in physics, but you like to master the concepts. Some of the content that I'm going through, if you could just understand half of the things that I go through, you will be more prepared than 90% of middle school science teachers. So it's very rare that the standards address some of these concepts, but they never really get to the heart and flesh. And today we're going to try to get into the heart and flesh of some of these concepts that are behind all of the standards. And also, this is for teachers looking for alternate ways to explain concepts to your students. So we will be introducing some different ways of explaining some of these things to your students. What we will cover, we're going to cover the content found in lessons 1.3.5 through 1.3.11 specifically. This is the very heart of Newton's Laws 1. And basically, we're going to look extensively at each of Newton's 3 laws of motions, and we're going to talk about how these laws actually fit together to make one cohesive theory of mechanics, really. And at the very end, we're going to have a question and answer session about the content found in these lessons. So without any further ado, let us get started. Newton's Laws 1, we're going to talk about Newton's 3 laws of motion. So first and foremost, let us address this question: why Newton's laws? Why? So Newton's laws, and specifically Newton's 3 laws, are perhaps some of the most profound things that could ever happen to science. Not just physics, but science. We need to understand the world in which Newton lived. In his world, he struggled with 3 main questions. The first question: what are the laws that govern how things behave? As he looked around, there was no real good explanation for why things were the way they were. And imagine trying to build a science without understanding some of these fundamental things for why things happen. There is no science without understanding laws that govern why things behave the way they behave. So he was wrestling with this question, and he was also wrestling with this question: if there are laws, are these laws universal? See, some of the things that were happening during Newton's time is that it was easy to explain something in one situation, but it didn't apply to another situation. So when he saw an apple fall from a tree and he saw the moon in the sky, during his time, the apple fell because that's what it did. All objects try to return to the earth, but all the things in space, they're not subject to the same laws on earth. And his question was, are there such laws that are so fundamental that they can apply at any point in time and any point in space? Are there laws that both agree to everything that happens on earth and everything that happens in space and in the heavens? This was his goal. And if there are such laws, what are they? So imagine if you were living in this time where you could explain nothing through some very fundamental laws, but you were able to finally get a hold of these golden chunks, the golden rules of how the world actually works. Imagine what you could do with these things. So the very first thing that you can do is that you can make predictions. So no longer did you have to the guess and check method. Let's build this and see how it works. Did it work well? Let's modify it. But you can say, this is how it's going to work because it obeys very specific laws. And this is really important. If you can make predictions, then you can build things specifically like machines, you can build cars, you can build airplanes, you can build trains. All of these things require fundamental laws or principles that you can rely on for them to work. All of us are comfortable in getting inside a car and having that car burn up gasoline and travel at very fast speeds and turn. We're all comfortable. Why? Because we can be comfortable with the surety of the laws upon which all of these pieces were built. We're all comfortable getting onto an airplane because we know that there are laws that do not change and that are universal. How scary would it be if in California the laws of aerodynamics were different than the laws of aerodynamics were different in California than they were in Colorado? So all of a sudden, once you pass that border, all of a sudden you plummet to your death. That would be a scary situation. But Isaac Newton said, no, there are universal laws that can be applied anywhere, from here to into space. So his laws were able to rationalize nature in such a way that some very amazing things could happen. And in fact, it's argued that Newton's laws are not just the foundation of physics, but all of science. So very, very powerful laws. And as it turns out, there's only 3 of them. With only 3 laws, the predictive powers of these 3 laws is we have not yet reached the limit to what we can do with these 3 simple laws. So with that, let's kind of talk about what these laws are. So starting with the very first law, Newton's first law of motion says objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted upon by an outside force. So basically, if you have an object like a piece of wood, it's at rest, well, it wants to stay at rest. And this is pretty intuitive, so this is kind of boring. But if an object is in motion, well, it wants to stay in motion. And if you think about this, this is counterintuitive because this is counter really what we experience every single day. Most of the objects we see moving, they stop. And students take all these ideas with us and they can look at something and say, well, every moving object will eventually stop. Because in our experience, that's what we experience on a daily matter. If you want to keep something moving, you need to keep applying a force to it. And this is not something new. It's actually, this is what people believed for thousands of years. They believed that all objects want to come to a stop, that the only way to keep something actually moving is that you need to constantly apply a force to it. Well, Newton says it's the exact opposite, that things always want to move if they're moving, and a force is needed to stop it. So a completely different way of thinking than the previous thought, which people held to for thousands of years. So when I say stay in motion, what I mean are two things. The first thing is that an object wants to stay moving the same direction, and it wants to stay moving the same speed. So if an object is changing directions, or if it's changing speed, speeding up or slowing down, then a force must be causing it. So we can look at the moon, and we see that the moon stays in motion orbiting the Earth. But it's constantly changing directions. So there must be a force behind that change in direction, and we all know that force is gravity. So this special type of motion is called uniform motion. And uniform should make you think of, well, uniforms. If you think about soldiers wearing a bunch of uniforms, they're all the very same uniform. So there's no change. And when we look at uniform motion, it's all the same type of motion. There's no change in motion. There's no speeding up. There's no slowing down. And there's no changing directions. Very special type of motion. So Galileo predicted that an object has what he called inertia. And this idea was adopted by Isaac Newton. And basically, this inertia is something that an object has that causes it to resist changes in motion. So the more inertia an object has, the more it actively resists speeding up, slowing down, or changing directions. And as it turns out, the more mass an object has, the more inertia it has. So mass is a measurement of inertia. So if we have a basketball, it's much easier to move than a truck, and a truck is much easier to move or accelerate than the Earth. So this is really Newton's first law, that he states how an object naturally wants to behave. If it's at rest, it wants to stay at rest. If it's in motion, it wants to stay in motion. And the only way to deviate is to apply a force. But this law does not specifically tell us how does a force affect motion. So this is why we need Newton's second law. So Newton's second law states that an object will change motion directly with the net force acting on the object and inversely with the mass of the object. So there's a whole lot in this law, so let us break it down. So Newton's second law pretty much says there's these three things: net force, change in motion, and mass. And these things are all related to one another. And instead of change in motion, I'm going to switch this to an equivalent term that I'll call acceleration. Acceleration is a change in motion. So these three things are related to each other. Now let's take a look at how a net force is related to an object's acceleration. So let us first define this word force, what is meant by it. So a force is an interaction between two or more things. Two things interact, they apply forces to each other. So we could think of this man and this chest, and he can look at the chest, he could talk to the chest, he can even think about the chest. But this is not what I mean by interaction. The physics term of interaction, what I really mean is a push or a pull. So here we have a wagon with all these boys pulling and pushing. So everywhere in this picture where we see either a push or a pull, there's some type of interaction. There's interaction between the boys' feet and the ground, interactions between their hands and the wagon. And in all of these interactions, since there's pushes and pulls involved, there's also forces involved. So a force is a physical quantity. A physical quantity simply means it can be measured. And if it can be measured, it has some unit attached to it. As it turns out, the units of force is this crazy unit, a kilogram meter per second squared. So if you saw part one, we saw that momentum has the units of kilogram meter per second. And we said that units are fingerprints that identify what we are actually talking about. So a kilogram meter per second squared is a fingerprint to identify force. But once we get to force And especially when you get to energy and power, these are all physical quantities, and the units get kind of crazy. So instead of sticking with these long units, kilogram meter per second squared, we simplify these units by saying whatever this is, we're going to call it a Newton, and we're going to give it the letter N. So 1 Newton is equivalent to a kilogram meter per second squared. And to get an idea how big a Newton is, imagine lifting an apple. The force it takes to lift that apple up is about 1 Newton. So that gives you an intuitive sense for what a single Newton is. So now that we looked at force, let's define what a net force is. So imagine you have this chest with a bunch of people pushing on this chest in a bunch of different directions. And we want to know, what is the net effect of all of these people pushing on this chest? In order to find that net effect, what we can do is we can take all these different pushes and we can add them together. And this net effect gives us this net force that we're talking about. So the question remains, well, how do you add together all these different pushes? Well, the nice thing is that force is a vector quantity. So all of these pushes can be transformed into little arrows. And if you saw part 1, we talked about how we can add all these arrows up. We take all these arrows and we align them head to tail. And then we notice we have a dangling tail here and then a dangling head here. We connect the dangling tail to the dangling head. And this little white vector is called the net force. So what's kind of neat is that here you have all of these people pushing on the chest, and you can simplify it to say, well, all of these people give a net force of one little guy pushing in one direction. So we have a teacher that actually uses this kind of concept in a classroom where she have a bunch of students pushing and pulling on a single desk, and then she has them freeze and she moves them up along the board and represents their pushes by vectors on the board, and then she adds up all of those vectors, so there's a net force, and then she has the students try to move that desk in a direction that's different than all of the directions of the people pushing on it. So it's a really interesting way of teaching this concept. So it's a really visual and a really good way to teach this concept about force. So one consequence is that a body will accelerate in the direction of the net force acting on the body. So the important part is not what is the individual force is doing, but what does the net force doing, and that tells us what's going to happen to the object. And objects, they move exactly in the direction of the net force. Also, a body will accelerate proportionally to the net force acting on the body. So what does that mean? Basically, it means if you have 3 different chests and 3 different guys pushing with different forces, we all know intuitively the one that's going to accelerate the fastest is the one with the greatest net force. And that is exactly what happens. Bigger the force, the faster the object is going to accelerate. So that is how net force is related to acceleration. So now let's talk about how all 3 of these are related. Let's pull in mass. Now, first question is, should mass have an effect? Well, if we remember Newton's first law of motion, and we say, well, the more mass an object has, the more inertia it has, and the more it resists changes in motion. Absolutely, mass is going to have an effect on an object's acceleration. So what is that effect? The heavier an object is, the more it will accelerate, or the less it will accelerate. Heavy bodies will accelerate slower than lighter bodies. So here, imagine you have 3 guys that are pushing with the exact same force, and they're pushing 3 different chests. Which one is going to accelerate the fastest? Intuitively, we know it's going to be the lighter one. That is the easier one to move. And sure enough, that's exactly what will happen. What's so interesting is that in the classroom, students can immediately identify it's the lighter one that's going to move faster. But once we start getting into problems where we're looking at 2 equal forces acting on 2 different objects, they forget about this entirely. One beautiful example is, imagine a foot kicking a soccer ball. It would seem as if something, well, I guess the foot applies a greater force to the soccer ball because the soccer ball goes flying. But what we see in Newton's third law, and what we will see, is that when a foot strikes a soccer ball, the ball will, in a sense, kick the foot with the same force as the foot kicks the ball. And if that's true, why is it that the ball goes flying out forward? Well, it comes back to this. The foot or the leg has a little more mass than the ball, so we see the effects of the force acting on the ball much more than we see the effects of the ball acting on the foot. And this is also true when something is interacting with the earth. A rock can fall off a cliff and strike the earth, and we don't see anything happen to the earth. But since the earth is so massive, it accelerates really slowly. So when we think about Newton's second law, we need to keep in mind that force is not enough to tell us about how an object will move. We also need to think about how massive is the object. So as the mass of an object increases, its acceleration gets small. And it turns out the Earth is incredibly massive. So any force applied to the Earth results in a very small acceleration. All right, so there was a lot of ideas in Newton's second law, and there's a lot in this little statement. So as it turns out, it's much handier to instead describe it in words, but to describe Newton's second law in an equation. And this is Newton's second law in an equation form, just 3 letters. We get rid of all those words and we replace it with 3 separate letters. So this says that acceleration is equal to the net force divided by its mass. So this is the acceleration of an object, and this is the mass of the object, and this is the net force acting on the object. So you may be more familiar with F equals ma, which is another way of rearranging this equation. But the reason it's not in F equals ma is because actually Newton's second law is more often used to find the acceleration than it's used to find the force. So it's not too often that Newton's second law is used to find force. So we put it in this form because it's used much more often to find the acceleration of an object. So when it comes to equations, especially when we're working with little 6th graders, there's a really wonderful tool to help your students work with these equations, especially when they're first exposed to it, called the physics triangle. And if I remember it at the very end of the session, I'm going to point to it. In the physics lab, there's both a video on how to use these physics triangles and a wonderful handout of how to use them. Great tool for students who have never seen or even talked about any of the algebra of manipulating these equations. But with one triangle, they can quickly identify the 3 equations that, using a little bit of algebra, you can manipulate this to solve for F, you can manipulate it to solve for mass, and in one triangle, you can do it. So this is a tool, wonderful tool that students can use, and the goal is to kind of wean them off so they can actually focus on the equations, because if they become dependent on the triangle, then all they know is the triangle. But if they use the triangle to write down the equations, enough times they'll memorize those equations and they won't need the triangle. So, but it's a beautiful tool, and I'll point to that at the very end of the session. So let us use this equation, because this equation, and I always say it, is the most important equation in all of science. It is the most important equation. Every single, yeah, it's more important than E equals mc squared, and it is, yeah, it is the equation for physics and engineering. So let us kind of take a look at how a problem looks. So imagine you have a guy who's pushing a chest that weighs 50 kilograms, has a mass of 50 kilograms, and he's pushing with a force of 50 newtons. And imagine there's no friction. Now, don't ask me how this man is pushing a chest on the floor with no friction, because that's a topic for another discussion. but just imagine he's pushing with a force. And he's pushing a total distance of 3 meters. And we want to know, if he's pushing with this force, how fast will the trunk be moving at the end of 3 meters? So to do this, the very first thing we need to ask ourselves is, what is the net force? This is always the first step. In this process, we say, what are all the forces acting on the object, and how do we add those forces together? So let us do just that. So right now, we see that there is no friction. And that means the only other force that will affect the motion of this chest is the applied force, this 50 newtons. So we can say that the net force is 50 newtons. So now we have the net force and we have the mass, and we can plug these into our equation. So A equals F over M, plug in 50 newtons for the force, plug in 50 kilograms, and this gives us 1 Newton per kilogram. But remember, a Newton is a kilogram meter per second. So the kilograms end up getting canceled out, and that gives us the right units for acceleration. So this object will accelerate 1 meters per second squared to the right. The reason I put to the right is because acceleration is a vector quantity and it needs a direction. So this chest will accelerate at this amount. Now, it's very easy for students to think this is the end-all be-all. And when students deal with Newton's second law, one of the common misconceptions is that the more you apply a force to an object, the faster it will go. So they equate how fast an object will go with how much force is acting on it, because this is our common experience. If you want to speed up, you need to run faster. You need to apply more force in your legs. If you want to drive faster, you need to step on the accelerator. So there's this common misconception that links speed with force. But what we see right here is that Newton's second law relates acceleration with force. And as it turns out, this chest, right when it starts out, will not be moving. It's only gradually after time that it will speed up. So whenever a net force is acting on an object, it is accelerating. So forces always, always, always cause an object to accelerate, not just speed up, or not just move a certain speed, but it causes an object to change its motion. So to illustrate that, I just want to go a little further and talk about what is the speed of the object after moving 3 meters. And if we know the acceleration and the distance, there's a nice little equation that we can plug these two values right into here. We know it's acceleration and distance. We can solve for velocity. So plugging that stuff in and calculating the stuff on the calculator will give us 2.5 meters per second. So up until now, I'm gonna keep going. So let's take a look at a second problem. So here you have this guy. He's pushing a chest that weighs 50 kilograms, and he's applying 50 newtons, and someone else is pushing the opposite direction with 75 newtons. And let's imagine there's no friction, just to make things simple. What is the acceleration of the trunk? So always the first thing we need to ask, what is the net force? What are all the forces acting on that chest, and how do we add them together? As it turns out, this is the question of physics. In almost all situations, we're trying to figure out what the net force is, because it's easy to calculate acceleration. You just divide by mass. So I would say 90% of physics is trying to find the net force acting on an object. But how do you find a net force? So here we have two vectors that are pointing in opposite directions. And if you saw part one, we said that whenever you have two vectors pointing in opposite directions, then you take the big vector and subtract the smaller vector. So we're going to take 75 newtons minus 50 newtons, and that's going to give us 25, and it's going to point in the direction of the bigger vector. So both of these guys can simplify to one little guy pushing with 25 Newton force, and that's our net force. So here we have a net force and we have a mass. Plug these in to Newton's equation, and it gives us 0.5 newtons per kilogram, or 0.5 meters per second squared, and it's going to be moving 2 to the left in the direction of the net force. So now, it's a few questions. In this previous example, we just saw two guys pushing in opposite directions, and one guy was pushing a little harder, so the chest moves a little bit. But what if you have these two guys pushing with the exact same force in opposite directions? What is the net effect? Well, if one person is pushing the chest in one direction and one person is pushing with the exact same force in the other, we can imagine that that chest is not going to move at all. It's not going to accelerate. All right, so that's not too difficult. But now imagine a situation where the chest is sliding along with a constant velocity on a frictionless surface. So, and it's obeying Newton's first law, and the object is in motion. Let's forget about how it got into motion, but it just is in motion. And it's moving along, and it's not stopping because for the moment there's no forces acting on it. There's no friction and there's no one pushing it. Now imagine at that moment, two of these guys jump and start pushing on that chest with equal and opposite forces. What would happen to the chest? Well, we just saw in the stationary case, there would be zero net force, so there'd be zero acceleration. And as it turns out, in the moving case, if they both applied equal and opposite force, there will be zero net acceleration. So what will the chest continue to do? It will continue to slide along with a constant velocity. And you'd say, Vincent, when would this ever happen? And I would say this happens more often than you think. If you're riding along the road in a constant velocity inside your car, the car may be traveling at constant velocity. If anything is moving at a steady speed, it means the total net force acting on that car is zero. Or if you take a chair and let's imagine you drag it across the floor at a constant velocity. If it's not accelerating, there's no net force acting on it. Well, how can it be if you're dragging a chair across the floor? And that's because we're leaving out one very important force, and that's the force of friction. More often than not, we forget about this force. But almost always, there's many forces acting on an object. In these past two examples, we ignored friction, but in real life, there's always friction involved. So if you drag a chair across the floor at a constant velocity, it means the force of friction is pulling the chair in the opposite direction that you're pulling on it in such a way that those two forces cancel each other out, so that the chair can actually move at a constant velocity. So, long-winded example, but it actually happens. So, as of this point, we have been looking at objects like a chest, and we are asking ourselves the question, how do forces affect that object? But we've not yet asked the question, okay, if the trunk or the chest has a force applied to it, or we've asked the question, how does the man affect the chest? But we've not asked the question, how does the chest affect the man? Because in any interaction, there's always two things interacting. And in interaction, if you're talking to someone, you need to be talking to someone else. And in physics, if a force is applied to one thing, that other thing also has an effect. So how do two objects interact? This is where we need Newton's third law. So Newton's third law says for every action, there is an equal and opposite reaction. So two important terms, action and reaction. So let's try to define those terms. So for every interaction, there is both an action and a reaction. And as it turns out, they're equal and opposite. So what does that mean? Well, remember what interaction is. An interaction is a push or a pull, or kind of like a force. So if we use that push or pull, then we see immediately that an action and a reaction are both forces. So when we think of Newton's third law, when we think of these actions and reactions, we need to think about forces, because an action is an action force and a reaction is an action force. So for every interaction, there's an equal and opposite force. So let's take a look at how this is applied in the most simple situation possible. A man who is simply standing there. Now, it may seem nothing is happening at all, but in fact, very astonishing physics is going on. So this man has two very overarching interactions that are happening at the same time. Unless we know physics, we wouldn't know to look for it, but in fact, there are two interactions. The first one comes between the interaction of his body and the ground. Right here, he's standing on the ground, so he's interacting with it. And also, this man is a big clump of mass, and the earth is a big clump of mass, and two clumps of mass are attracted to one another. So there's also this interaction of gravity happening. So let's take a look at both of these two interactions. Starting with the interaction of gravity, we all know that the man is being pulled to the earth by gravity, but what we often don't think of, and what students often forget when they're thinking about this situation, is that the man is mass and the earth is mass, so the earth must also be attracted to the man. Students can clearly see, okay, the man is attracted to the earth, but they forget that the earth is attracted to the man. So if he's being pulled down, is he causing the earth to be pulled up? And the answer to that question is yes. And according to Newton's third law, for every action there's an equal and opposite reaction. So he actually pulls up on the earth with the exact same force. We call one the action of him being pulled down, and that is equal and opposite to the reaction of the earth being pulled up. And together, both of these form the interaction of gravity. Now, what about this interaction between him and the floor? Well, the man is standing on the floor, so he's applying weight, and we can actually measure that weight by standing on a scale. A scale measures how much force this man is pushing down on the ground. And according to Newton's third law, he's interacting with the ground with an equal and opposite force. So there is this other force pushing up on him. And we call this force the normal force. And if one is the action, one is reaction, both of these form together to give us the interaction between the man and the ground. So let us tally all this up. So on the right, I'm going to look at the forces acting just on the man, and on the left, I'm going to look at the forces acting on the ground. So his weight is acting on the ground as he's pushing on the floor, and he's got this interaction, or this reaction force, this normal force pushing him up. And he's got gravity pulling him down, but his body also pulls the earth up because of the same gravity. So if we ignore what's happening on the ground and say, here are these forces acting on the man, let's add up the forces acting on his body. We have gravity pointing down and the normal force pointing up. And if we add these two vectors together, we will see that they cancel each other out. So there's a zero net force acting on the man, which is a good thing. So if you're standing there, you're not accelerating. And this is a good thing. Otherwise, if one was bigger than the other, you would be either accelerating up or down, whichever one was greater. So now let's look at a situation where the man jumps off of the ground, and we're interested what happened the very moment he left the ground. Well, if we had a scale, we could measure the effect of his weight. If you stand on a scale and jump off of it, your weight spikes. And according to Newton's third law of motion, the equal and opposite must happen for the normal force. So the normal force grows as a result of his jumping. But what about gravity? Well, his mass doesn't change, so gravity should remain the same. So now if we take the forces acting on the man and we add them together, we will see something astonishing. There is a net upward force, and this is actually how the man jumps off of the ground. And the question is, where does this extra force come from? And the surprising result, and this blows my mind even when I think about it, that the force that actually lifts the man off the ground comes from this normal force being greater than the force of gravity pulling him down. So it's actually the force coming from the ground that lifts him up off of the ground. It's kind of, I mean, I don't know how you make sense of this, but the only way to actually see if it's true is looking at the vectors. Another way of thinking about it is imagine you're out there floating in space, and imagine trying to jump in space. Well, you couldn't, because you have no floor to push off of. So you need a floor in order to jump. So that's pretty much what it says. But even more interesting is what's happening with the ground. Now take a look at the vectors acting on the ground. We see that we have these two vectors, and if we add them together, we have a net downward force. And as it turns out, this is equal and opposite to the force acting on the man. And if we remember from Newton's second law, whenever an object has a net force acting on it, it will accelerate in that direction. So basically, this means that by jumping off of the ground, the man will cause the earth to accelerate downward. So this begs the question, will my sleep be disturbed if someone halfway across the world is jumping up and down? And the obvious answer is no, my sleep's not going to be disturbed. Why not? Because when you remember during Newton's second law, the more massive an object is, the less it will accelerate. And the Earth is extremely massive, so it's not going to accelerate very much. But if I were to exaggerate these effects, this is similar to what it would look like. So we notice as the man is moving up, the Earth moves down, and as the man moves down, the Earth moves up. And this is simply a consequence of Newton's third law of motion. So another way of saying Newton's third law is, instead of for every action there's an equal and opposite reaction, we can say if something moves one direction, something else must move the other direction. So this may sound, just another example. Here's a rocket, and always the big question is, how do you move something in space? How do rocket scientists do it? Well, they remember Newton's third law of motion. So if we want to apply a force to the rocket in this direction, we must apply a force to something else in the opposite direction. And as it turns out, that force comes by pushing out all of this exhaust. So if we really think about it, if we compare Newton's third law to the conservation of momentum, they sound very, very similar. And as it turns out, they're pretty much the same thing. They're just two ways of looking at the exact same thing. So Newton's third law looks at forces involved, whereas the conservation of energy, or conservation of momentum, we look at the momentum involved. So if we take our little rocket example, if we look at the force acting on the rocket up, well, that's going to equal the force of all those particles being shot out the back of the rocket. And we can look at the momentum of the rocket moving up, and that's going to equal the momentum of all those particles moving out the back of the rocket. And it gives us the same motion. All right, so this about summarizes Newton's three laws of motion. So now I guess I want to open it up to any questions. Just to say, we had a lot of content to go over, so if there's any questions, do feel free to ask. Right. One question, do you have any suggestions for helping students differentiate between velocity and acceleration? Yeah, that's an excellent question. So, I guess the reason this is difficult is because it's difficult to see acceleration. So, I guess. One of the suggestions I would put out is to one simple activity you can put up would be to create a ramp, simple ramp by laying down a board and on top of a table, and then measure the average velocity of a simple ball rolling down a ramp at different heights on that ramp. So don't vary the angle of the ramp, but vary the position that that ball rolls down, and measure the average velocity. And as you see, the farther the ball moves, the faster it will be going, so it will have a faster average velocity. And I guess it's a concept to show that the ball speeds up. I guess the ball speeds up because they'll get a different measurement every single time. It's common to believe that if you just drop it down the ramp, you can measure its speed, but its speed is constantly changing at every single point down that ramp. I don't know if it answers the question, but acceleration is, I guess, it's a difficult concept for students because it's difficult to see. We can easily see something move, but it's not so easy to see it accelerate. So yeah, I guess I don't know if I answered your question, but it's the best I have right now. All right, any other questions? Okay, so looks like we don't have any other questions. So next time, we're going to cover Newton's Laws 1, the last couple of lessons in this unit, and we're going to cover forces and interactions, cover both contact and non-contact forces. And that will be on December 10th, 2015, so just a week from today and at the same time. So to access either this recording or this PowerPoint to go over some of the concepts, both the PowerPoint and the recording will be posted up on the See the Change USA WebMoto group, and the recording will be also posted on the physics lab. So let me show you real quick how you can access the Edmodo group. So let me change the share. Okay, so here is the physics lab. If you click on resources, there's a tab that says links. And from here, there's a link to the See the Change USA Edmodo group. Click on that. All right, and if you do not have an account, you can easily create an account by clicking I'm a teacher, and all you need is an email address and a password, and then you can sign up for free. But I'm just going to log in with my information. All right, and that link will take you right here after you have created your account. And if you'll have a join request, so send join request, go ahead and send that join request, and you will be added to the group. But since I'm already a part of the group, I don't need to send a join request. And by clicking on the See the Change USA, and then after you join the group, you will be added to these small groups. So if I click on Newton's Laws 1 over on the far left, there's this little folders button. And what we see right here, there's this content training. And here is last week's, or 2 weeks ago, here's the webinar from last week, and then here is the PowerPoint that is used. So this video and PowerPoint will all be posted right here, and it will also be posted on the physics lab. There's also one more tool that I talked about. I talked about the physics triangle. So starting at catalog from the page, if you click on catalog and then go down here to teacher support, there's this tab that says Physics Tips and Tricks. Click on that. And here's the video for using the physics triangle. And then there's also a printable that you can give out to your students so that they can read and learn about it. And that'll teach you how to use the different physics triangles for all the different equations that you'll find in our curriculum. Open this back up. Okay. So both those things will, you can find the recording on the physics lab, and you can find both the recording and the PowerPoint on the See the Change USA Edmodo group. And if you have any questions, do feel free to either email me or Laura, whom you all know. You can get me at vincent.weiss@seethechangeusa.org or laura.horvath@seethechangeusa.org, or feel free to give us a call at 719-602-4440. All right, and if there are no other questions, we want to thank you all for your time, and we hope to see you back again next week. So have a wonderful day, and we will see you all later.